What you will learn in this story: the difference between cybersecurity engineering versus architecture, and why architecture drives long-term security success. How to think like a security architect: business context, system context, technical design. Why documentation is a strategic tool for communication, decision-making, and training. How the NIST Cybersecurity Framework serves as the building code for security programs. The 7 core security domains: IAM, endpoint, network, application, data, monitoring, incident response, and how they integrate. How to design with risk and failure in mind to build resilient systems. Strategies for cross-functional collaboration and gaining stakeholder buy-in. A phased approach to enterprise-wide security transformation with measurable results. The career path of a cybersecurity architect and why developing systems thinking is critical. How architectural thinking becomes the foundation for mastering advanced security domains. Chapter 3: The Master Builder's Blueprint. The elevator doors opened on the 32nd floor at precisely 8 a.m., revealing Marcus Rivera carrying his worn leather portfolio and a steaming cup of coffee that had already survived 2 security checkpoints. As chief security architect for one of the nation's largest financial institutions, Marcus had learned that successful security transformations began not with technology implementations, but with a single sheet of paper and the ability to translate complex technical requirements into business language that executives could understand and approve. This morning's presentation would determine the future of his organization's cybersecurity posture. The board of directors, still reeling from news of yet another major financial institution suffering a catastrophic breach, had allocated $50 million for a comprehensive security transformation. Marcus had 6 months to design and implement an enterprise-wide security architecture that would protect assets worth over $200 billion while enabling the digital innovation initiatives that drove business growth. The challenge facing Marcus represents the fundamental distinction between cybersecurity engineering and cybersecurity architecture. Engineers excel at implementing specific technical controls, configuring firewalls, deploying endpoint protection software, and tuning intrusion detection systems. Architects think at a different level entirely, designing comprehensive systems where individual components work together to achieve strategic objectives that no single technology could accomplish alone. This architectural mindset requires a fundamental shift in perspective that many cybersecurity professionals struggle to develop. While engineers focus on making systems work correctly, architects must simultaneously consider how systems will fail and design resilient structures that continue to protect critical assets even when individual components are compromised. This distinction is not merely academic. It determines whether organizations build security programs that scale effectively or create complex technical environments that become increasingly difficult to manage and defend. The architect's perspective: thinking in systems. Marcus settled into the conference room 30 minutes before the scheduled board presentation, spreading architectural diagrams across the polished mahogany table. Each diagram represented months of stakeholder interviews, technical analysis, and strategic planning, distilled into visual representations that would either secure executive support or send him back to the drawing board for another redesign cycle. The first diagram, labeled Business Context, showed the organization as a single entity surrounded by external parties: customers, regulators, business partners, and threat actors. This highest-level view demonstrated how cybersecurity initiatives directly supported business objectives rather than simply implementing technical controls for their own sake. Every security investment shown in subsequent diagrams could be traced back to protecting specific business relationships or enabling specific business capabilities. This business-centric approach reflects a crucial architectural principle that separates successful security programs from expensive technical implementations that provide minimal value. Security architects must understand not only what threats exist, but which threats actually matter to their specific organization's business model, risk tolerance, and strategic objectives. A community bank faces different threats than a cryptocurrency exchange, and their security architectures must reflect these differences rather than implementing generic best practices that may not address their actual risk profile. The second diagram, titled System Context, decomposed the business entity into major functional areas: customer-facing applications, internal business systems, data storage and processing capabilities, and administrative infrastructure. Each functional area connected to others through well-defined interfaces that showed both information flow and trust boundaries. This level of detail enabled stakeholders to understand not only what the security architecture would protect, but how protection mechanisms would integrate with existing business processes. Professional security architects develop these visual representations not as documentation exercises, but as thinking tools that help identify security requirements that might otherwise be overlooked. The process of creating system context diagrams forces architects to consider questions that don't arise during technology-focused planning sessions. What happens when the customer authentication system is unavailable during peak business hours? How should the organization respond when regulatory reporting systems detect data integrity violations? Which business processes require real-time security monitoring, and which can tolerate delayed analysis? The third diagram, labeled Architecture Overview, showed the technical components that would implement the security requirements identified in the higher-level diagrams. This level included specific technologies, protocols, and integration points, but organized them according to their contribution to business objectives rather than their technical characteristics. Firewalls, intrusion prevention systems, and endpoint protection solutions were grouped by their role in protecting customer data, not by their vendor or deployment location. Marcus had learned through hard experience that presenting technical architectures without establishing business context first was a recipe for confusion and rejection. Board members needed to understand why the organization was investing in specific security capabilities before they could evaluate whether the proposed technical implementation was appropriate. The hierarchical diagram structure allowed him to present complex technical designs while maintaining clear connections to business value throughout the presentation. Documentation as a strategic weapon. As board members began filtering into the conference room, Marcus reflected on the evolution of his documentation approach over 15 years of cybersecurity architecture roles. Early in his career, he had viewed architectural documentation as a necessary evil, something to be completed after the real work of designing technical solutions was finished. He now understood that documentation was the primary tool for influencing organizational decision-making and ensuring that security initiatives received adequate resources and executive support. Effective architectural documentation serves multiple audiences with different requirements and expertise levels. Technical teams need detailed specifications that enable accurate implementation and ongoing maintenance. Business stakeholders require high-level summaries that demonstrate value and justify continued investment. Compliance teams demand comprehensive control mappings that prove regulatory requirements are adequately addressed. Risk management functions expect quantitative analysis showing how proposed security measures reduce organizational risk exposure. The challenge lies in creating documentation systems that serve all of these audiences without becoming so complex that they provide value to none of them. Marcus had developed a layered approach where each diagram could stand alone for its intended audience, while linking to more detailed information when additional depth was required. Business context diagrams included hyperlinks to detailed technical specifications. System context diagrams connected to risk assessment documentation. Architecture overview diagrams linked to implementation schedules and cost projections. This approach recognized that architecture documentation is fundamentally about communication rather than simply recording technical decisions. The most elegant technical architecture provides no value if stakeholders cannot understand its benefits or if implementation teams cannot translate design concepts into working systems. Professional architects spend as much time refining their communication techniques as they do developing technical expertise. Version control and change management become critical when architectural documentation serves as the authoritative source for organizational security decisions. Marcus maintained all architectural artifacts in a centralized repository where changes were tracked, reviewed, and approved through formal processes. This discipline ensured that the documented architecture remained synchronized with implemented systems and that proposed changes were evaluated for their impact on the overall security posture. The documentation also served as a training resource for junior team members who needed to understand not only what security controls were implemented, but why specific design decisions were made and how they contributed to organizational objectives. By including decision rationale and alternative approaches that were considered and rejected, the architectural documentation became a knowledge management system that preserved institutional memory and accelerated the development of architectural thinking skills. The Framework Foundation, building codes for cybersecurity. 20 minutes into his presentation, Marcus introduced the concept that would anchor the entire security transformation: the NIST Cybersecurity Framework as the architectural equivalent of building codes. Just as construction projects must comply with established standards for structural integrity, electrical systems, and fire safety, cybersecurity programs must implement comprehensive frameworks that address all aspects of organizational risk management. The NIST Cybersecurity Framework organizes cybersecurity activities into 5 core functions that parallel the life cycle of effective security programs. Identify establishes the foundation by cataloging assets, understanding business context, and documenting governance structures. Protect implements safeguards that ensure delivery of critical services. Detect develops capabilities to discover cybersecurity events quickly and accurately. Respond takes action regarding discovered cybersecurity events. Recover maintains resilience and restores capabilities that were impaired during cybersecurity events. This framework structure provides several advantages over ad hoc approaches to cybersecurity program development. It ensures comprehensive coverage by requiring organizations to address all aspects of cybersecurity management, rather than focusing exclusively on technical controls or reactive measures. It enables consistent communication by providing standardized terminology that stakeholders across different functional areas can understand and apply. It facilitates maturity assessment by establishing clear categories for evaluating program effectiveness and identifying improvement opportunities. Marcus explained how the framework would guide technology selection and implementation priorities throughout the security transformation. Rather than selecting security tools based on vendor marketing claims or popular industry trends, the organization would evaluate each potential investment according to its contribution to specific framework functions and subcategories. This approach would prevent the accumulation of overlapping capabilities that provided redundant protection while leaving critical gaps unaddressed. The Identify function would begin with comprehensive asset inventory and risk assessment activities that established baseline understanding of what needed protection and why. This phase would include business impact analysis to prioritize security investments, governance structure development to ensure ongoing program management, and supply chain risk management to address third-party vulnerabilities that could compromise internal security measures. Protect function implementation would focus on access controls, awareness training, data security, information protection processes, maintenance activities, and protective technology deployment. This phase would establish the primary defensive measures that prevent unauthorized access to critical assets and ensure that authorized users can perform their responsibilities safely and securely. Detect function capabilities would include anomalies and events detection, continuous security monitoring, and detection process management. These capabilities would provide the situational awareness necessary to identify security incidents quickly and accurately, while minimizing false positive alerts that could overwhelm response capabilities. Response function development would encompass response planning, communications procedures, analysis capabilities, mitigation measures, and improvement processes. These capabilities would ensure that discovered security events are contained and resolved quickly, while capturing lessons learned that improve future response effectiveness. Recover function implementation would address recovery planning, improvement activities, and communication strategies that restore normal operations after security incidents. This phase would ensure business continuity while incorporating security enhancements that prevent similar incidents from recurring. The framework approach also provided a structure for measuring program effectiveness and demonstrating value to executive leadership. Each function included specific outcomes and success criteria that could be tracked over time and compared to industry benchmarks or organizational targets. This measurability was essential for justifying ongoing security investments and identifying areas where additional resources or process improvements were needed. Integration across the enterprise. The collaboration challenge. The most technically sophisticated security architecture provides no value if it cannot be successfully implemented within the constraints of existing organizational structures, processes, and technologies. Marcus had learned this lesson through several painful experiences where elegant security designs failed because they required changes that stakeholders were unwilling or unable to make. Successful security architecture requires deep collaboration with specialists across multiple technical domains. Database administrators understand data storage, backup, and recovery processes that directly impact security monitoring and incident response capabilities. Network administrators control the infrastructure that security tools depend on for communication and coordination. Application developers make design decisions that determine whether security controls can be effectively integrated into business processes. Each of these functional areas has its own priorities, constraints, and success metrics that may not align naturally with security objectives. Database administrators prioritize performance and availability, which may conflict with security monitoring requirements that add processing overhead. Network administrators focus on reliability and capacity management, which may not accommodate the additional traffic generated by security tools. Application developers emphasize functionality and user experience, which may be degraded by security controls that add complexity or delay to business processes. Professional security architects develop collaborative approaches that acknowledge these competing priorities while identifying solutions that advance security objectives without compromising other functional requirements. This requires understanding each functional area's technical constraints and business objectives well enough to propose security implementations that enhance rather than hinder their effectiveness. The key insight Marcus had developed over years of cross-functional collaboration was that security architects must become fluent in the languages and concerns of other technical specialties. When discussing security requirements with database administrators, architects must speak in terms of query performance, storage optimization, and backup recovery procedures. When working with network administrators, the conversation should focus on bandwidth utilization, routing protocols, and infrastructure redundancy. Application security discussions require understanding of development methodologies, user interface design, and business process integration. This multilingual approach enables security architects to identify implementation approaches that satisfy security requirements while working within the operational constraints of existing systems and processes. Rather than demanding changes that other functional areas view as unreasonable or unnecessary, architects can propose solutions that stakeholders recognize as beneficial to their own objectives. The Enterprise Security Transformation Marcus was presenting required coordination across more than 30 different functional areas, each with its own technical requirements and operational constraints. The success of the initiative would depend as much on stakeholder management and change facilitation as on technical design expertise. Marcus had structured the implementation approach to deliver visible benefits to each functional area early in the process, building momentum and support for more complex integration activities that would come later. Network security improvements would reduce the burden on network administrators who currently spend significant time investigating false alarms and responding to minor security events. Endpoint security enhancements would simplify device management for help desk staff who supported thousands of employee workstations. Application security tools would provide development teams with automated testing capabilities that improve code quality while reducing manual security review requirements. The 7 domains, comprehensive security architecture. As his presentation entered its final phase, Marcus introduced a conceptual framework that would organize the technical implementation of the security transformation, 7 core domains that collectively addressed all aspects of enterprise cybersecurity. This domain structure provided a logical way to organize complex security programs while ensuring comprehensive coverage of all attack vectors and defensive requirements. Identity and access management serves as the foundation for all other security domains by establishing who is authorized to access organizational resources and under what circumstances. IAM systems authenticate user identities, authorize access to specific resources, and maintain audit trails that enable investigation of security events. Modern IAM implementations extend beyond simple username and password systems to include multi-factor authentication, role-based access controls, privileged access management, and continuous authentication that adapts to changing risk conditions. Endpoint security protects the devices that users employ to access organizational resources, including laptops, mobile phones, tablets, and increasingly, Internet of Things devices. Endpoint security tools provide anti-malware protection, configuration management, patch deployment, and behavioral monitoring that identifies compromised devices before they can be used to access sensitive resources or spread malware to other systems. Network security controls the communication pathways that connect organizational resources and enable business processes. Network security tools include firewalls that filter traffic based on predetermined policies, intrusion prevention systems that block known attack patterns, network segmentation that limits the spread of successful attacks, and monitoring systems that provide visibility into network traffic patterns and anomalies. Application security addresses vulnerabilities in the software systems that support business processes and store sensitive data. Application security includes secure development practices that prevent vulnerabilities from being introduced during the software creation process, runtime protection that defend applications during operation, and testing tools that identify security weaknesses before applications are deployed to production environments. Data protection ensures that sensitive information remains secure throughout its life cycle, from creation through disposal. Data protection includes encryption that renders data unreadable to unauthorized parties, data loss prevention tools that monitor and control data movement, backup systems that enable recovery from security incidents, and classification systems that ensure appropriate protection based on data sensitivity. Security monitoring aggregates security telemetry from all other domains to provide comprehensive situational awareness and coordinated incident response. Security information and event management systems collect logs from thousands of devices and applications, correlate events that may indicate security incidents, and provide dashboards that enable security analysts to monitor organizational security posture in real time. Incident response provides structured processes for containing, investigating, and recovering from security events. Incident response includes preparation activities that establish response procedures and communication protocols, detection and analysis capabilities that determine the scope and impact of security incidents, containment and eradication measures that stop ongoing attacks and remove malicious artifacts, and recovery processes that restore normal operations while incorporating lessons learned. The power of this domain-based approach lies in its recognition that enterprise security requires integrated capabilities that span all 7 areas. Weakness in any single domain can compromise the effectiveness of controls in all other domains, while strength in each domain reinforces and amplifies the protection provided by the others. Marcus's architectural design showed how security telemetry would flow between domains to provide comprehensive visibility and coordinated response capabilities. Identity and access management systems would feed authentication and authorization data to security monitoring platforms. Endpoint security tools would report device status and suspicious activities to incident response teams. Network security controls would enforce access policies defined by IAM systems while reporting policy violations to monitoring systems. This integration would enable security analysts to investigate incidents by correlating evidence from multiple domains, providing a complete picture of attack progression and impact. Rather than managing 7 separate security programs with limited visibility into overall effectiveness, the integrated architecture would function as a unified defense system where each domain contributed to comprehensive organizational protection. Risk-based architecture, designing for failure. The final element of Marcus's presentation addressed the fundamental principle that distinguished cybersecurity architecture from other IT architecture disciplines, the assumption that all systems will eventually be compromised. While traditional IT architects design systems to work correctly under normal conditions, cybersecurity architects must design systems that continue to protect critical assets even when individual components are compromised or fail entirely. This risk-based design approach begins with comprehensive threat modeling that identifies potential attack vectors and evaluates their likelihood and potential impact. Rather than attempting to prevent all possible attacks, risk-based architectures focus defensive resources on the threats that pose the greatest risk to organizational objectives. This prioritization ensures that limited security budgets provide maximum risk reduction while accepting that some less critical vulnerabilities may remain unaddressed. Threat modeling also informs architectural decisions about system segmentation, access controls, and monitoring capabilities. High-value assets receive additional layers of protection and more intensive monitoring, while lower-value resources may rely on baseline security controls that provide adequate protection at lower cost. This differentiated approach enables organizations to achieve comprehensive security within realistic budget constraints. The architectural design Marcus presented included explicit failure analysis, showing how the security program would continue to function when individual components were compromised. If the primary authentication system failed, backup authentication mechanisms would maintain access control for critical business processes. If network monitoring systems were compromised, Endpoint-based detection capabilities would continue to identify suspicious activities. If primary data centers were unavailable, geographically distributed backup systems would maintain business continuity. This failure-resistant design required significant additional complexity compared to architectures that assumed perfect component reliability. Each critical function required backup capabilities, monitoring systems needed redundant data collection mechanisms, and communication systems needed multiple pathways to prevent single points of failure. The additional investment was justified by the dramatic reduction in business risk that resulted from resilient security architectures. Risk-based design also influenced technology selection criteria by emphasizing security features that would function correctly under attack conditions. Security tools that required constant internet connectivity to function would be less valuable than tools that could operate effectively in degraded network environments. Monitoring systems that depended on centralized databases would be less resilient than distributed systems that could continue operating when individual nodes were compromised. The presentation concluded with quantitative risk analysis showing how the proposed security architecture would reduce organizational exposure across multiple threat scenarios. Rather than promising perfect security, Marcus demonstrated how each architectural component would reduce the likelihood and impact of specific types of attacks while providing measurable improvements in overall risk posture. Implementation strategy. From blueprint to reality. The board approved Marcus's proposal with an enthusiasm that surprised even him. Within 2 weeks, he was leading a cross-functional team of 40 security professionals, IT specialists, and business stakeholders through the complex process of translating architectural designs into operational reality. The implementation strategy reflected lessons Marcus had learned from previous large-scale security transformations. Rather than attempting to implement all 7 security domains simultaneously, the plan divided the work into phases that would deliver measurable value while building organizational capability and stakeholder support for subsequent phases. Phase 1 focused on foundational capabilities that would support all other security domains: comprehensive asset inventory, risk assessment, governance structure development, and basic security monitoring. These capabilities would provide the situational awareness and decision-making frameworks necessary for effective implementation of more advanced security controls. Phase 2 implemented core protective measures, enhanced identity and access management, endpoint security deployment, network security improvements, and basic incident response procedures. This phase would establish the primary defensive capabilities that would prevent the majority of common attacks while providing the infrastructure for more sophisticated security tools. Phase 3 deployed advanced detection and response capabilities, comprehensive security monitoring, threat hunting capabilities, automated incident response, and integration between security domains. This phase would transform the organization from reactive security management to proactive threat identification and response. The implementation approach also emphasized knowledge transfer and capability development within the organization. Rather than relying exclusively on external consultants to implement security tools, the project included comprehensive training programs that developed internal expertise for ongoing system management and continuous improvement. Professional development became a crucial component of the transformation strategy. Team members received training in security architecture principles, framework implementation, risk assessment methodologies, and project management techniques. This investment in human capital ensured that the security program would continue to evolve and improve long after the initial implementation was complete. 6 months later, as Marcus presented the transformation results to the same board that had approved his initial proposal, the quantitative improvements were impressive. Security incident response times had decreased by 75%, successful phishing attacks had dropped by 90%, and compliance audit findings had been reduced to 0. More importantly, the organization had developed internal capabilities for continuous security improvement that would protect against emerging threats and changing business requirements. Professional implications. The architect's career path. The successful security transformation established Marcus as a recognized leader in cybersecurity architecture, leading to speaking engagements at industry conferences and consulting opportunities with other organizations facing similar challenges. However, the most valuable outcome was the development of architectural thinking skills that would serve him throughout his career regardless of changing technologies or evolving threat landscapes. Cybersecurity architecture represents a distinct career specialization that requires different skills and knowledge compared to cybersecurity engineering or management roles. Architects must develop systems thinking capabilities that enable them to understand complex interactions between technical components, business processes, and organizational structures. They must become proficient in visual communication techniques that enable them to present complex technical concepts to stakeholders with varying levels of technical expertise. The role also requires continuous learning and adaptation as new technologies, attack techniques, and business requirements emerge. Cloud computing, artificial intelligence, Internet of Things devices, and quantum computing will create new architectural challenges that require fresh approaches to established security principles. Professional architects must stay current with these developments while maintaining deep understanding of fundamental concepts that remain constant across technological changes. Career advancement in cybersecurity architecture typically involves progression from tactical implementation roles to strategic design positions with broader organizational impact. Senior architects may become responsible for security standards development, organizational policy creation, or industry leadership roles that influence cybersecurity practices across multiple organizations. The skills developed through cybersecurity architecture experience also transfer effectively to other career paths within cybersecurity and technology leadership. The systems thinking, stakeholder management, and strategic planning capabilities that successful architects develop are valuable for roles in cybersecurity management, technology consulting, and executive leadership. For cybersecurity professionals interested in developing architectural capabilities, Marcus recommended starting with small-scale design projects that demonstrate systems thinking and stakeholder communication skills. Contributing to architecture documentation, participating in design reviews, and volunteering for cross-functional projects provide opportunities to develop architectural experience within existing roles. Formal education and professional certification support career development in cybersecurity architecture, but hands-on experience with real organizational challenges provides the most valuable learning opportunities. Professional associations, industry conferences, and peer networking relationships enable architects to learn from others' experiences and stay current with evolving best practices. The foundation for advanced security domains. As Marcus reflected on the lessons learned during his organization's security transformation, he recognized that the architectural framework and implementation approach they had developed would serve as the foundation for exploring specialized security domains in greater depth. Each of the 7 core domains represented a career specialization with its own technical requirements, professional certifications, and advancement opportunities. The architectural perspective provided a crucial foundation for advanced study in any security domain because it emphasized the interconnections and dependencies that determine overall program effectiveness. Understanding how identity and access management integrates with endpoint security, network security, and security monitoring enables professionals to design solutions that work effectively in complex enterprise environments rather than simply implementing point solutions that may not provide comprehensive protection. The framework-based approach to cybersecurity program development also provided a structured method for continuous improvement and adaptation to changing requirements. Rather than reacting to individual security events or technology trends, organizations with mature architectural foundations could evaluate new requirements and capabilities according to their contribution to overall security objectives. The next phase of professional development would involve deep exploration of specific security domains, beginning with identity and access management as the foundational capability that enables all other security functions. Understanding IAM architecture, implementation approaches, and operational considerations will provide the foundation for advanced study of endpoint security, network security, application security, data protection, security monitoring, and incident response. Each domain would require its own case studies, technical deep dives, and professional application examples. But the architectural thinking framework developed through this comprehensive security transformation would provide the conceptual structure for organizing and applying domain-specific knowledge effectively. The journey from cybersecurity engineering to cybersecurity architecture represents more than a change in job responsibilities. It requires a fundamental shift in perspective from tactical problem-solving to strategic systems design. This shift enables cybersecurity professionals to address the complex, interconnected challenges that define modern organizational security while building programs that provide lasting protection against evolving threats. Marcus's story demonstrates that successful cybersecurity architecture requires equal measures of technical expertise, business understanding, and communication skills. The most elegant technical designs provide no value if they cannot be successfully implemented within organizational constraints and stakeholder requirements. The most comprehensive security programs fail if they cannot demonstrate measurable business value and secure ongoing executive support. The architectural mindset represents the bridge between cybersecurity theory and cybersecurity practice, enabling professionals to translate abstract security principles into concrete organizational capabilities that protect critical assets while enabling business success. This bridge becomes increasingly important as cybersecurity challenges grow in complexity and organizational dependence on digital systems continues to expand. Understanding cybersecurity architecture provides the foundation for advanced specialization in any security domain, while developing the strategic thinking skills that enable career advancement into senior technical and management roles. For cybersecurity professionals seeking to maximize their impact and career potential, developing architectural thinking capabilities represents one of the most valuable investments they can make in their professional development.
If you enjoyed this video, be sure to subscribe to the channel for the latest updates.